record on this computer?
I believe that Dylan, you found that button.
Okay, now we're good. Yeah, so I'll just repeat my little intro, I guess. So I'm a senior majoring in astronomy. I'm the one who's been organizing this event, and I am hoping that this can become a sort of yearly tradition. So anyway, as I was what I was leading up to is, before we start, if someone could tell the group, because I certainly don't have to tell you guys if you're STEM students, what pi is. Oh, well, you can read off the paper, sure, but like, what is it? Why is it significant?
Constant to measure certain properties in circles.
Exactly right. Yeah. Well, and so those certain properties in particular, we'll get to in a second. But the first question is, well, why do we have a whole day for this mathematical constant? Why do we celebrate Pi Day? And the answer is, it started in 1988 with a man named Larry Shaw, who worked at the San Francisco Exploratorium, which is like the science museum there, equivalent to like the Museum of Natural History for my New Yorkers in the room. And this was an initiative sort of to promote like engagement with, just engagement with STEM in general, in which, we'll see how pi is not just the circle constant. Due to the fact that it's a circle constant, it appears all over math and physics. But then it really sort of gained a lot of recognition in 2009 with the United States House of Representatives officially recognizing it as a holiday. Not the kind where you get the day off from work or anything, unfortunately, but a lot of people are sort of exposed to Pi Day through their middle or high schools, because they'll do a special activity in their math class, or they'll have competitions. You can recite the most digits of pi, similar to what we'll be doing after this presentation. And then UNESCO gave it the additional title of the International Day of Mathematics. And that's very cool, just in my opinion, because up until then there had been like sort of a few competing like international days of mathematics, but now this one is the definitive one. And the actual logo of it has these 3 yellow dots, and then the dots on this side go like 1, 4, 1, 5, 9 to, they're going with the digits of pi. So, and of course, if anyone has any questions during the presentation, feel free to, interrupt me or raise your hand. So pi is the ratio of a circle's circumference to its diameter, right? So any circle, doesn't matter how big it is, it's always the same. It's an example of the same sort of like idealized shape. Of course, there are no perfect circles in nature. So anytime when we try to measure pi with a real circle, we'll always get only an approximation. But, we have tools in mathematics like geometry and, more complex analytical tools that allow us to define pi with perfect precision. And a lot of the times we actually are more interested in the radius of a circle than its diameter, but pi helps us there too when we look at the area of a circle. First, if we took a square with a side length r, that square will have a radius of r, or will have an area of r squared, and the circle area is just pi times that. It's the same deal when we're looking at the surface area of a sphere. Because you can take a sphere, if you see here where I've highlighted, and you can sort of stretch it out, to take it and like, reshape it into a cylinder with like the open ends on the top and bottom, and you haven't changed the area of it at all. And we know how to do cylinders because you can unroll them into a rectangle with a height of 2r, right? Because that's just the diameter of your original sphere. And the top side of the rectangle, which is shown in yellow, was it was originally this yellow circle, the top sort of perimeter of the cylinder. And we know that like it's a circle, so it's obviously just going to be pi times the diameter, or 2 pi times the radius. And in fact, a lot of people, in the mathematical community, I don't know that this is really a debate anywhere else, but they, prefer using 2 pi over having like pi itself, and they refer to that as tau, because that's the Greek letter that has like one leg. It looks like pi, but it only has one leg instead of two. And tau is just defined as being equal to 2 pi, and they say that that makes a lot of formulas simpler. But pi is the one that caught on. It's really just a matter of taste which you use. And there are definitely areas where pi makes more sense, like in the pi r squared formula. And then the volume of a sphere, we have 4/3 pi r cubed. And that, illustrates a nice sort of geometry fact, which is when we're dealing with stuff in 2 dimensions, the area of a circle, when you scale it up by a certain factor, the area will increase by that factor squared because it's 2-dimensional. And then when we're using spheres, that's 3-dimensional, so it goes by r cubed. And one more, why call it pi at all? This notation first caught on due to the etymology of the Greek word perimeter, which, I mean, that's a word we use in English, but it's a Greek word, and it started with the letter pi, because that was the sound that the Greeks used to make the p sound, like the letter P. So other ways we see pi appearing, right? Like, as I said, in places that don't necessarily seem like they have obvious connections to circles, like in physics, the top of this list. I realize this may be a little small for you guys to read in the audience, but I'll just tell you a few of these things. On the top, the cosmological constant, which is a very important number in astrophysics. It tells us, or cosmology really, I should say. It tells us about how quickly the universe is expanding, and it's got a little pi there in the numerator. Heisenberg's uncertainty principle, that tells us how possible it is to accurately measure the position and the momentum of any given particle, because it actually turns out that there is a limit to that. You can't know both of those quantities perfectly. And that is related to pi because you have a 4 pi here in the denominator, which is like the lower limit of the accuracy that you can achieve. And then the rest of this list, there's things like pendulums, there's stuff about Coulomb's law, about electrostatic attraction or repulsion or whatnot. And other places in math where it happens to pop up, like there's the very famous Riemann conjecture, which, that could have its own talk. That's not pertinent to this, but it essentially is a question about a given function called the Riemann zeta function. And that looks like adding up an infinite sum of fractions where the denominators of those fractions are just all of the integers raised to a certain power, and the power that they're raised to is the number that you're plugging into the function. And for every even number where you do this, the result is a power of pi raised to some exponent, then multiplied by some coefficient. And if you're familiar with factorial, where like 5 factorial is like 1 times 2 times 3 times 4 times 5, it's actually possible to extend that concept to non-integer values, even though there's no real way to intuitively visualize that. And that's called the gamma function, where the gamma of n is defined as just being n minus 1 factorial. And when we do that, when we take the gamma of 1/2, which is just like saying the factorial of minus 1/2, that comes out to be the square root of pi. We know nowadays, like we obviously have sheets of paper here in the room telling us the value of pi to great accuracy, but we didn't always know, like we at first just had to estimate, really, just by looking at a circle or like taking a string, wrapping it around the edge and seeing how much longer it is than the diameter, so that gave us, the ancients, they had estimates between 3 and like 3.2. Like Archimedes came up with an estimate that was between like 3.13 and 3.15. You gotta give him some credit for that. But that whole process, what that entailed was, some very complicated geometry of trying to calculate the perimeters of polygons with a very large number of sides, because those, of course, are similar to circles. And then Newton came along and changed the game when he realized that you could do infinite series based on trigonometry. Because, well, so trigonometry, what do we think of that as? It's the study of, the name implies that it's the study of triangles, but really it's more just generally the study of angles. And we have a particular function in trigonometry called a tangent, right? And whenever we have a right triangle, and then you can think back to your high school math when you learned this, a right triangle where the angle is 90 degrees, the side labeled perpendicular and the side labeled base have a special relationship to the angle that's listed here in orange, such that the tangent of that angle is equal to the ratio of the perpendicular and the base. And so we can just do the inverse function of the tangent, which is the arctangent, and that to get back the angle itself if we don't know the angle and we're only given the perpendicular and the base. You know, so when I guess I accidentally skipped this slide. I was like pressing, the next button too quickly. But places where pi is used, if you're familiar with like the unit circle, and the way that you measure angles in radians rather than degrees, so 360 degrees is a full circle, but we can also call that 2 pi radians, because based on our established understanding that the circumference is 2 pi times the radius. So therefore we can think of 1 radian as if you're traveling a distance equal to the radius across like the arc of the circle. And when we throw complex numbers into the mix of that, you can do the given angle that you're traveling from the x-axis, like up around the circle counterclockwise. You can plug that in when you raise another irrational number e, which is just as interesting as pi, really, and could have its own talk as well, to the power of I times phi, where phi is the angle that you put in. That equals, this is the very famous and often recognized as often described as the adjective they use, I think, is elegant, is cosine phi plus I sine phi. And when you make that angle pi, that means you're traveling halfway around the circle. And that brings you to the location of -1 on the unit circle. And if we've shown now that e to the power of I pi is -1, then we can create this formula e to the I pi plus 1 equals 0. And that is what is really the kicker for a lot of people, because it brings the 5 most important constants in math together without any crazy stuff, just addition and exponentiation. So that's why when I get to tangent, some of you may also know that that's equal to the sine of an angle divided by the cosine of an angle, just for context. But let's say that the angle that we're given is 45 degrees or pi over 4 radians, right? So that is not just going to be a right triangle, it's going to be a right isosceles triangle where, the perpendicular equals the base, right? So therefore, we know that pi over 4, right, which is the angle that we started with, must be equal to the arctangent of 1, because what's the ratio of the perpendicular and the base when they're equal? It's, that's, it almost goes without saying in a way. But that still leaves the issue of calculating it. So I'm not going to go into how all these formulas are derived necessarily, but you can just take my word for it that the arctan of x is equal to this big long sum of x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, right? It's all the odd numbers, and it's alternating plus and minus, right? So let's just plug in 1 where we had x before, and that gives us this formula for that's pi over 4. So and then if you wanted to just multiply the whole thing by 4, you'd get 4 minus 4 thirds plus 4 fifths minus 4 sevenths, right? And that doesn't look like it has anything to do with circles, but there's this connection between the odd numbers, really, and number theory, which is what that realm is, and geometry and trigonometry. You have other infinite sums doing similar things. You have an infinite product, which is really cool, where it's alternating even numbers like on the top and odd numbers on the bottom, in the, when you take all these fractions and you multiply them together. Of course, you could never evaluate that, you could never take all of the numbers on the top and multiply them with each other and multiply all the numbers on the bottom and multiply them with each other, because that would be infinity over infinity. Right, like that's getting back to the whole deal of pi is an irrational number, right? There's no way to express it as the ratio of two integers. And the consequence of that is that its digits never repeat. Well, they may repeat like a few times, like you may see like, oh, we had like 5, 6, 7, 9, 4 in one place, and you have that same set of 5 digits later on. But it's not like other fractions where it's like 0.33333, and that's the same thing like forever. You have products with nested square roots. I really don't know how this one's derived. I think it's called Vieta's formula, actually. Where each layer there's an addition, each term as you move to the right, there's an additional layer. You have what are called continued fractions, where it's the same sort of deal, but each denominator in the fraction contains another fraction within it, right? So here I'm starting with 3, obviously, and then this term represents all the stuff that comes after the decimal point. You could also have 4 divided by a number that's a little bit more than 1, which makes sense because pi is a bit less than 4, really. And we see another connection to odd numbers as well as just the numbers in general. You can use what's called, I think, a machine formula or a machin formula, which is basically one of like something that looks like this with multiple arctan terms, because it turns out that this first formula that I was telling you is extraordinarily inefficient. You would need like 5 billion terms to get like 10 correct digits. It's possible to do way better. You can have even an infinite sum of arctans where the denominators of the fractions that you're inputting into the arctan functions are every other Fibonacci number. And then lastly, pi is equal to the sum of the arctans of any 3 numbers where a plus b plus c is equal to a times b times c. So for example, 1 plus 2 plus 3 equals 6. That's actually a factorial, right? So when we saw before that arctan of 1 is pi over 4, that actually tells us, without having to do any calculation, that the arctan of 2 plus the arctan of 3 must be equal to 3 pi over 4, if you think about it like that. But the 2 most important formulas for modern computations that try to set like new world records of the most digits of pi use these 2 formulas. And I'll actually start with the one on the bottom. That's called the Chernovsky formula. And it's so ugly. Like, it's this infinite sum. I didn't explain the sigma notation, but that's what this means. Like, you take the term that's here and you plug in k for every value from the bottom that's listed here from 0 up to infinity, and you add up all the results. And then you multiply by 12, and then you invert the fraction. But it turns out that for each term of this sum, you actually get 14 new correct digits of pi. And then, well, they want to make sure the calculation is correct, right? So they do this one on the top, which is the Bailey-Borwin-Plouffe formula. And what you'll notice, and although this is a bit of an oversimplification of how it actually works, it's a term in the parentheses multiplied by 1 over 16 to the k. And let's say you were doing math in base 16, as computers often do. And, pi is really just a sum of like, well, when we're doing it in base 10, it's 3 plus 0.1 plus 0.04 plus 0.001, right? But if you're doing it in base 16, it's the same deal where each new digit is representing a value that is, an order of 16 times smaller than the previous one. So this expression in the middle, essentially what it's doing is it's giving us an expression for the kth digit of pi in base 16. And you don't have to do this big sum, right? Because when you do the big sum, that gives you pi itself, but you could just calculate any base 16 digit that you want. So they'll calculate the base 16 digits close to the end of their calculation. And if it matches with what they got from this formula, they know it's right. And this has gone extraordinarily far in the last few decades. You can see when computers were invented around 1950, right? Up until then, they had to do it either by hand or with, the first sort of mechanical calculators. The furthest they got was about 700 digits by the turn of the 20th century, although there was actually a mistake that was discovered at the 527th digit. That was only corrected when, the next people came along and they were using the mechanical calculators. And then it's gone up at this extraordinary rate. And this logarithmic scale on the y-axis, you'll notice that the current record is 100 trillion digits. And that was done by Google, unsurprisingly, with all their massive computing power. But it's still important to remember that that represents exactly 0% of the total value of pi. And now we'll move on to a sort of prelude to what we're getting to, which is the sport, which some people sort of think of it as, or the art or the skill of memorizing pi. And there are some people who have really gone to extraordinary lengths. The world record as of 2020 is 123,456 digits. I do get asked occasionally, oh, are you interested in being the world record? No, 7,000 is enough for me. You also have, and it's from various interesting places in the world. The first title you see is from Sweden. I'll move the Zoom thing so you can actually see the numbers. Then, Japanese Akira Haraguchi, the Chinese Chao Lu, and then another Swedish Jonas van Essen, American Sebastian James, and Indian Rajan Mahadevan, all tied at 100,000. And the Guinness certified world record actually is, comes from 2015, and that's because the Guinness team, they have very, strict criteria, like they have to have their representatives there, which not everyone can facilitate, so, this is what if you just look up pi memorization world record, this is usually what you'll find, but when you do a little more research, you find that people haven't gone further, and it really took off starting in the late 70s and early 80s. And of course, at one time, before the mechanical calculators and the computers, it actually was possible to memorize all the computed digits of pi in existence. It was only, as I mentioned, the mistake that was found at one point in the 527th digit, the sort of founder, I sort of like to think of pi memorization, actually memorized all of those digits at that time, and then when the mistake was found, he rememorized the new stuff coming after 527. But a lot of people then ask me too, like, well, how do you do this? And there are several methods, and someone was asking me earlier, well, are there certain like languages that it's easier to do this in? And the answer is, well, if you look at Japanese, and Chinese is, basically the same to a similar extent, these languages are packed with homophones, right? So you have tons of words that sound like the words for your numbers. So you can basically make stories, by stringing, sets of words together. And by remembering the story and saying the words out loud, you're saying words that sound like the numbers, and that prompts you to remember what you were originally going for. The example of that is given here. There's also, for people who sort of just want to dip their feet in, there's the phenomenon of the poem, which is a poem where each word has a length such that you count up the words in it, and that corresponds to a digit of pi, right? Like how I want a drink. And this has been done out to 10,000 digits, with a book you can buy on Amazon, Not Awake, and it even continues into the subtitle, A Dream Embodying Pi's Digits Fully, so that's like, so Not Awake is like 3, 1, 4, and then A Dream, like 1, 5, and it's very clever. I don't know if anyone's ever actually used that to memorize that number of digits. There's also what's called the mnemonic major system, where you take the numbers 0 through 9, and you associate each one with a set of consonants. So 0, right, it starts with a z sound, so they'll associate that with the sound z, but also s, like z, s, because it's the same sort of sound when you make it. 1 is corresponding to other sounds, and then by putting these sounds together, you make words, and as you sound out the words, that's what's reminding you of the numbers you started with. And to compound on all of this, there's also the well-known method of loci, which goes back to antiquity. When Roman senators wanted to memorize hours-long speeches, they would take each part of the content that they were working with, and they would create like a visual space in their brain. They also refer to this as like the memory palace, if you've watched like Sherlock on BBC or whatever. And they think of themselves like walking through that space, and each part of that space reminds them of a certain piece of information that they were trying to remember. They sort of make a set of associations in their brain. But I don't really use any of these methods. What I do is, if the slide will advance, I have here, this is the first 1,000 digits in groups of 5, and I have a friend at Yale, his name is Ari Essenfeld. You can Google him. you know, and he's gone even further than I have, as far as I know. But you know, it's often done in this way. He uses groups of 4, you know, some people even use groups of 3, you know, and you repeat it to yourself enough times, you know, like maybe you try writing it down, you know, like, and you find things about the digits that are memorable for some reason, like all the places where there's 2 in a row or 3 in a row, and one place even 6 in a row. That's you know, like right here, I can go 0, 0, 1, 1, 3, 3, you know, or I remember that you know, these 2 groups of both start with 7, like 7, 2, 4, 5, 8, 7, 0, 0, 6, 6, you know, and the way I think about it really is song lyrics, you know, which most people probably have memorized several thousand words worth of, you know, where each group of 5 is a word, and then 4 groups of 5 is a line, and then 5 groups of 20 is a verse or like a stanza. So to cap off, you know, I will say that we're not just celebrating Pi Day, but we're also celebrating Einstein's 145th birthday. And we are unfortunately, you know, commemorating the life of Stephen Hawking, who died 6 years ago on Pi Day. But I will take any questions if you have any. And yeah, thanks for listening to my presentation. Yeah, Ben.
So thinking about, like, you probably know the common errors in linguistics are like, you make substitutive errors a lot, where the one consonant is in another consonant place, or I think they call them Tapetus errors, where they just swap like one syllable with different ones, different songs. And I'm wondering, like, for example, if you're reciting pi and you mess up somewhere, is it more likely to be that you've maybe deleted a number, added a new one, swapped numbers around, swapped entire verses? Maybe you start with the Elston Barrett verse. What are the types of errors you maybe use the most frequently, and then what do you hear about other people saying those?
Well, I don't know what other people, but that's a very good question. Yeah, sometimes I'll see like numbers being flipped. Sometimes I'll see like accidentally replacing one number for another, especially when it comes to groups of 5 that are very similar to each other, like maybe they're only off by one number. You know, and I also will sometimes jump ahead or behind by a factor of 100 or 1,000. You know, because I'm thinking about you know, in the sort of structure, like, and sometimes, and those 2 issues can also intersect. Like sometimes I'll have a group of 5 that's similar to another group of 5 that occurs exactly 200 digits ahead. You know, and afterwards I can actually point a couple examples of that out to you if you're still interested in that. But yeah. And then other errors, like just if you haven't practiced in a while, you can just misremember. You know, that's like, you know, I'm not going to give an example of that because I don't want to prompt myself into saying that a bit later. But yeah. Yeah, Justine?
Right. So what are your opinions?
I feel like I've heard of it. I'm not really so is it the game like that is just on in a web browser where it's a little guy running along and you have to type in digits of pi to give him like new platform to stand on? Yeah. It's cool to a certain extent, but it doesn't necessarily it's sort of not very forgiving if you need some time to think. You know, like if you get sort of stuck somewhere and you have to try and remember like, oh, what comes next? Right. So yeah. So if those are all the questions, then without further ado, we will move on to the recitation portion.
You went upstairs.
Oh, well, if someone doesn't mind going upstairs and yeah, thanks, Ben. Oh, yeah. Oh, well, wait, don't close it yet, because maybe some people want to come from upstairs.
Yeah, okay. I talked to the deck crew and I told them to make sure people walk quietly up and down the stairs.
Okay. And what I'm gonna do is I'm also gonna move the computer, hopefully keeping it attached to the TV screen. Oh, no. Okay.
I've got another question.
Oh, yeah, go
When you
ahead.
get to the end of this, like, three people tied for third place, why do, like, they have a 10% chance of getting third place all themselves, why do you not?
So what's the question?
Yeah, like, when you get to.
Sure, I guess.
Maybe they did make that.
Alter the daughter off.
That's possible.
I'm just surprised at all the records.
Exactly 100,000. I have to assume it was like.
Oh, I can unplug the computer. That should help.
You know.
No, you come in here.
Thank you.
I'm spending my jacket.
Well, I can't, I don't know.
Eric.
I know 11.
Yeah. Well, you gotta memorize now. It took 3 digits to get to the moon, you can probably get off with them starting 7,000, right?
Yeah, right.
Yeah.
So, yeah, we have our, so there are a couple things I do want to say first before we get into the recitation. I have these just like on a bullet list on my phone. So first of all, everyone's welcome to participate. You know, there's no minimum number of digits. You know, I'm not gonna say like, oh, you only know 2. Okay. Yeah. Yeah, and this is also not a competition, right? Like, it's more for people to just demonstrate their, you know, like if they've taken the time in the past, like if they put in any effort in the past, you know, like whether that's because they're a STEM student and they're interested in it, or because, you know, they participated in some pie competition at their middle school and they still remember some of that. You know, this is something I've done for several years as a hobby. You know, and putting any effort into it really puts you ahead of like 99% of people. So, and then what I'll say is when people are in the midst of reciting, you know, obviously we want to minimize the amount of like side conversation and, you know, preferably like silence your cell phones as well. And then when people come up here, we will ask them, oh, well, maybe they'll want to sit down actually. Yeah, maybe I'll get a chair in that case. So there'll be a chair here. Oh, whoops, come on, reconnect. Oh, well, we don't really need the screen anyway at this point. But, you know, we'll ask them if they want us to point it out to them if they make a mistake. And like, you know, invite them to correct themselves. Or if they would rather not be interrupted, in which case, after we're finished, we'll play the recording back and see if what they said matches what was on the page. And of course, you know, if one of the judges thinks they noticed a mistake, then they can mark that on the sheet. You know, once I start, as you all probably know from reading the announcement on Slack, the door will be closed. So you will want to decide before that happens whether you want to be in here or upstairs, because you know you'll sort of be stuck with it. So that means if anyone needs to go to the bathroom, if the bathroom's been repaired, if it's in like working order, you know, that's a thing you can do. And one more thing is we have a bunch of forms from the website of the Pi World Ranking List, which is a real website. You know, and if you decide that you want to try to be featured on that website, you know, you need to have 2 witnesses who are 18 or older and are not related to you. So, you know, and for the World Pi Ranking List, you have to certify that you said a certain number of digits without any outside help and also without making any errors. So even though I will allow you to correct yourself, the World Pi Ranking List will not, unfortunately. You know, I really don't like that rule just because, you know, you can be cut off and then you don't have the opportunity to, you know, continue, you know, like all the effort that you put into the digits that come after wherever you messed up sort of goes to waste. And we also, although you guys will know when I'm done because there won't be any more paper. But, you know, other than that, you know, we won't applaud until the person says they're done. because, someone may stop to think for a while and, if we start plotting, that could throw them off. So I think that is everything. And, you have a question?
The question what I got was, if you, I'm not being pessimistic here.
Yeah.
Just in case, if you make an error, are you gonna keep going?
I am gonna keep
And
going,
at the
yeah.
end, just tell you the errors.
Yeah, so I will say that I would rather just keep, not have the sort of interruption limit. No, I mean, reciting pi is hard, like as someone who, as I've said, has spent a good deal of time with it. It is, it's commendable, really, like if you feel for, like, if maybe the reason you're drawn to it, or a reason that someone could be drawn to it, is that they, they sort of feel a degree of significance associated with, these numbers that really are embedded into the fabric of the universe as we know it. So there's, I'll give a little shout out, I guess, to a YouTuber named Stand Up Maths, actually, who just like recently got who lives in the UK, who just recently got a whole group of people together, a group of 400 volunteers actually, and for 6 days they sat doing calculations and they came up with 139 correct digits of pi. But the last digit that they calculated was wrong. So there have been mistakes in calculations, there are mistakes in recitations, that's just how it goes. Who wants to go first? Does it appear that maybe I'm the only person? I don't know,
I'll go.
Yeah. Let's welcome Justine up to the stage.
Ignore now, right?
No, well, just when I start.
Yeah, just need time.
And before we start, I actually will go upstairs once more to remind everyone that if they want to see the stuff, they're about to miss it.
I'm not doing very many digits, so now is your time to decide if you guys want to also do it.
No.
I am no 5, so.
Sixth grade, we did this, like, reciting celebration.
I guess,
Your teacher with one of my.
Good one.
I did 101. Yeah, we did much like these, everybody else, and I was doing much.
What did I miss? What did I miss?
When I was in fifth grade, my fifth grade teacher held a competition for Bible.
Oh, yeah.
And he provided us with a little slip of paper, with 100 digits on it. So
Yeah.
like, just try and do as many of these as you can. And I did 101, thinking that everyone else only got 100 digits.
Oh, that's
So and I got beaten by somebody who did 102.
Okay. So yeah, Justine, whenever you're in, and if the judges are ready, yeah. Although I'm gonna be judging as well, although I don't exactly need a piece of paper. So, I guess everyone else has them.
Right? Yes, I'll start. 3.141592653. That's
It's pretty good. Yeah.
You do have a 10% chance of getting.
Would you like to guess the next digit?
From what I remember from what you said, I'm gonna go with 8.
That's correct.
Yeah.
Oh. Here are the other papers, actually, if anyone wants one, that,
Okay.
Sure.
I will try.
Oh, awesome. Okay.
Let's see if you can.
Please say 3.
4, no.
3.141592653589799. 3238 4626 433 83279 50288 41971 582. Stop me if I'm.
Oh, so
messing
you
up.
want to be corrected?
Yeah,
Yeah,
stop me.
that was wrong.
Okay,
Got up to 7.
I got to, okay, show me.
Well, so if you can correct yourself though, like if you look at it, then you're correcting. Okay.
There you go.
Okay, well, that's pretty good. Oh, yeah, go ahead.
This one back in.
I think the highest I was at is like 50. I'm sorry to whoever's backpack I picked.
Which one was it? Was it this one?
I don't know.
You could kick it away.
Minus 2 points. Or plus 2 points. Okay.
Okay. 3.141592693. Wait a minute. Fuck.
So you're good if you want to correct yourself.
3.141592653589793233846264338327950232995028832795023383279502338 and I think
So that was correct?
8.
Ah,
God damn it.
you got 4 digits past Ben.
Yeah, I thought I could do more.
So I'll just give away this last sheet of paper since it seems that I'm the only remaining.
I'll do.
Oh, you want to come up? Awesome.
I'll do one.
You'll do one.
Yeah.
Oh, he's good. Oh, he's gonna do one.
Recitation.
Yeah.
Okay.
To be fair. 30 digits past.
Wrong.
When do I start?
Is it
First
when-
now?
Whenever you want.
And do you want to be interrupted or you want to keep going?
Yeah, interrupt me.
Okay.
3
I'm
point,
afraid you made it.
Yeah.
no, 3.1415926535897939445923098164062862089986280 3482534211706798221
Correct?
10% chance.
3.
Nah.
Yes.
You beat the fifth grader.
Huh?
You and Alice were both off by 1 on your 10% chances.
Yeah.
Beat my 5th grade dentist.
Let's
Yeah.
go.
Yeah.
Now,
Yeah, like the key test where like if you're doing this for real, they take away your paper 24 hours before the
oh, yeah.
presentation. Or are you allowed to like look,
What, sorry, what's the question?
like how like looking at the paper and not allowed?
Oh, that's,
just, like,
yeah, that's fine.
Okay.
Yeah. I guess the only issue is maybe you get a little more preparation than someone else, but again, it's not a competition. I do just need to plug my computer in, so I'm hoping that this will reach all the way to that outlet. That's too bad.
Session card.
Anyone have one of those?
Um,
Well, I'll, what am I gonna do? Because I want it to be like with me in the video.
Okay, you got it right now.
I mean, you can recite tonight.
You can just pull the stool back a little bit.
Yeah, I guess I don't need to be in the video. As long as it records the audio.
In the video, just,
You read the video.
Oh, someone has the extension cord. Love that.
You lied.
Yeah.
Welcome to Fuertes Observatory. It's your first time here.
Great. This is a really long extension cord. Oh, yeah, but the one thing I'll say before I start is you'll notice the 6 9s, and that is actually
Why?
that is actually sort of referred to as the Feynman point, because there's an anecdote that Richard Feynman said that he would like to memorize pi up to that point and then just say like, and so on. It's not, there's not really any good evidence that he ever said it. It's actually a misattributed quote from someone else. But yeah, yeah.
For beta.
Yeah, so, I'm closing the door. So, again, thank you all for being here, and I hope you, enjoy, I guess, you know, what you're about to see. Three point 141592653589793238462643383283279. 5028841971693993751058209749445. 2307816406286208998628034825342. 1170679821480865132823066470938444. 60955052822317253594081217450284111745027019385 11055596446294895493038196442 881097566593 34461 28475 64823 37867 83165 27120 19091 45648 56692 34603 48610 45432 66482 13393 60726 02491 41273 72458 70066 06315 58817 48817 2092096282925 4091715 36436 78925 90360 01133 05305 48820 46652 13841 46951 94151 16094 33057 27036 5759591 953 09218 61173 81932 61179 31051 18548 07446 23799 62749 56735 18857 52724 89122 79381 83011 94912 98336 73362 4406566 43086 0213949 46395 224737190 7021798 60943 73277 05392 17176 29317 67523 84674 81846 76694 05132 00056 81271 45263 56082 77857 71342 75778 96091 73637 17872 14684 40901 22495 34301 46549 58537 10507 96279 68925 89235 42019 9561 12129 02196 08640 34418 15981 36297 74771 30996 05187 07211 34999 999 8372978 04995 10597 31732 81609 63185 95024 45945 55469 0302 64252 23082 55344 68503 52619 31188 17101 00031 37838 75288 65875 33208 38142 06171 77669 14730 3592 53490 42875 54687 31159 56286 38823 53787 59375 19577 81857 78053 21712 26806 61300 19278 76611 19590 92164 20189. Now I'm gonna take a drink of water. Three 25720 10654 85863 2786 59361 52381 82796 82303 01952 03530 18529 68995 77362 25994 13891 24972 17752 83479 13151 55748 57242 45415 06959 50829 53311 68617 27855 88907 5093 81754 63746 49393 19255 06040 09277 01671 13900 98488 24012 85836 16035 63707 66010 47101 81942 95559 61989 46767 83744 94482 55379 77472 68471 04047 53464 62080 46684 25906 94912 93313 67702 89891 52104 75216 20569 66024 05803 81501 93511 25338 24300 35587 64024 74964 73263 91419 92726 04269 92279 67823 54781 63600 93417 21641 21992 45863 15030 28618 29745 55706 74983 85054 94588 58692 69956 90927 21079 75093 02955 32116 53449 87202 75596 02364 80665 49911 98818 34797 75356 63698 07426 54252 78625 51818 41757 46728 90977 77279 3000 81647 06001 61452 49192 17321 72147 72350 14144 19735 68548 16136 11573 52552 13347 57418 49468 43852 33239 07394 14333 45477 62416 86251 89835 69485 56209 92192 22184 27255 02542 56887 67179 04946 01653 46680 4986 27232 79178 60857 84383 82796 79766 81454 10095 38837 86360 95068 00642 25125 20511 73929 84896 08412 84886 26945 63424 19652 85022 21066 11863 06744 27862 20391 94945 04712 37137 86960 95636 43719 17287 46976 46575 73962 41389 08658 32645 99581 33904 78027 59009 94657 64078 95126 94683 98352 59570 98258 22620 52248 94077 26719 47826 84826 01476 99090 26401 36394 43745 53050 68203 49625 24517 49399 65143 14298 09190 65925 09372 21696 46151 57098 58387 41059 78859 59772 97549 89301 61753 92846 81382 68683 86894 27741 55991 85592 52459 53959 43104 99725 24680 84598 72736 44695 84865 38367 36222 62609 91246 0051 24388 43904 51244 13654 97627 80797 71569 14359 97700 12961 60894 41694 86855 58484 06353 42207 22258 28488 64815 84560 28506 01684 27394 52267 46767 88952 52138 52254 99546 66727 82398 64565 96116 35488 62305 77456 49803 55936 34568 17432 41125 15076 06947 94510 96596 09402 52288 79710 89314 56691 36867 22874 89405 60101 50330 86179 28680 92087 47609 17824 93858 90097 14909 67598 52613 65549 78189 31297 84821 68299, 89487, 22658, 80485, 75640, 14270, 47755, 51323. 79641, 45152, 37462, 34364, 54285, 84447, 95265, 86782. 10511, 41354, 73573, 95231, 13427, 16610, 21359, 69536. 23144, 29524, 84937, 18711, 01457, 65403, 59027, 99344. 03742, 00731, 05785, 39062, 19838, 74478, 08478, 48968. 33214, 45713, 86875, 19435, 06430, 21845, 31910, 48481. 00537, 06146, 80694, 91927, 81911, 97939, 95206, 14196. 63428, 75444, 06437, 45123, 71819, 21799, 98391, 01591. 95618, 14675, 14269, 12397, 48940, 90718, 64942, 31961. 56794, 52080, 95146, 55022, 52316, 03881, 93014, 20937. 62137, 85595, 66389, 37787, 08303, 90697, 92077, 34672. 21825, 62599, 66150, 14215, 03068, 03844, 77345, 49202. 60541, 46659, 25201, 49744, 28507, 32518, 66600, 21324. 34088, 19071, 04863, 31734, 64965, 14539, 05796, 26856. 10055, 08106, 65879, 69981, 63574, 73638, 40525, 71459. 10289, 70641, 40110, 97120, 62804, 39039, 75951, 56771. 57700, 42033, 78699, 36007, 23055, 87631, 76359, 42117. 31251, 47120, 53292, 81918, 26186, 12586, 73215, 79198. 41484, 8291, 64470, 60957, 52706, 95722, 0975, 67116. 72291, 09816, 90915, 28017, 35067, 12748, 58322, 28718. 35209, 35396, 57251, 21083, 57915, 13698, 82091, 44421. 00695, 10334, 67110, 31412, 67111, 36990, 86585, 16398. 31501, 36990, 86585, 16398. 31501, 97016, 51511, 68517. 14376. 57618, 35155, 65088. 49099, 89859, 98238, 73455. 28331, 63550, 76479, 18535. 89322, 61854, 89632, 13293, 30898, 57064, 20467, 52590. 70915, 48141, 65498, 59461, 63718, 02709. 81994, 30992, 44889, 57571, 28289, 05923. 23326, 09729, 97120, 84433, 57326, 54893, 82391, 19325. 97463, 66730. 58360, 41428, 13883, 03203. 82490, 37589, 85243, 74417, 02913, 27656. 1809, 3773, 444, 0300707, 469, 21120, 19130, 20330, 38019. 762, 110, 1100, 44929, 32151, 60842, 44485, 96376, 69838, 95228, 68478, 31235, 52658. 21314, 49576, 85726, 24334, 41893, 03968. 64262, 43410, 77322, 69780, 28073, 18915, 44110, 10446, 82325, 27162. 01052, 65227, 21116, 60396. Six 30925, 47110, 5575, 37634, 66820, 65310, 98965. 26918, 62056, 47693, 12570, 58635, 66201, 85581, 00729, 36065, 98764. 86117, 91045, 33488, 50346, 11365, 76867. 53249, 44166, 80396, 26579, 78771, 85560, 84552, 96541. 26654, 08530, 61434, 44318, 58676, 97514, 56614, 06800. 70023, 78776, 59134, 40171, 27494, 70420, 56223, 05389. 94561, 31407, 11270, 00407, 85473, 32699, 39081, 45466. 46458, 80797, 27082, 66830. 63432, 85878, 56983, 05235, 80893, 30657, 57406, 79545. 71637, 75254, 20211, 49557, 61581, 40025, 01262, 28594. 13021, 64715, 50979, 25923, 09927, 96547, 37612, 55176. 56751, 35751, 78296, 66454, 77917, 45011, 29961, 48903. 04639, 94713, 29621, 07340, 43751, 89573, 59614, 58901. 93897, 13111, 79042, 9782H. 56475, 03203, 19869, 15140, 28708, 08599, 04801, 09412, 14722, 13179, 47647, 77262, 24142, 54854, 54033, 21571. 85306, 14228, 81375, 85043, 06332, 17518, 29798, 66223. 71721, 59160, 77166, 92547, 48738, 98665, 49494, 50114. 65406, 28433, 66393, 79003. 97692, 65672, 14638, 53067, 36096, 57120, 91807, 63832. 71664, 16274, 88880, 07869, 25602, 90228, 47210, 42317. 21186, 18204, 19000, 42296. 61711, 96377, 92133, 75751, 14959, 50156, 60496, 31862. 94726, 54736, 42523, 08177, 03675, 15906. 73502, 35072. 83540. 56704, 03867, 43513. 62222, 47715. 89150, 49530, 98444, 89333, 09634, 08780. 76932, 59939, 78054, 19341, 44737, 74418, 42631, 29860, 80998, 88687, 41326, 04721. 56951, 62396, 58645, 73021, 63159, 81931, 95167, 35381. 29741, 69729, 47867, 24229, 24654, 36680, 09806, 76928. 23828, 06899, 64004, 82435, 40370, 14163, 14965, 89794. 09243, 23789, 69070, 69779, 42236, 25082, 21688, 95738. 37986, 23011, 59377, 64716. Um. 51228, 93578, 60158, 81617. 55782, 97352, 33446, 04281. 51262, 72037, 34314, 65319, 77774, 16031, 99066, 55418. Um. 76397, 92933, 44195, 21541, 34189, 94854, 44734, 52738. 31624, 99341, 91318, 14809, 27777, 10386, 38773, 43177. 20754, 56545, 32207, 77092, 12019, 05166, 09628, 04909. 26360, 19759, 8281, 61332. 31666, 36528, 61932, 66863, 36062, 73567, 63035, 44776. 28035, 04507, 77235, 54710, 58595, 48702, 79081, 43562. 40145, 7180. 62464, 36267. 93, no, 94, 561, 27531, 81340, 78330, 33625, 42327, 83944, 97538, 24372, 05835, 31147, 71199. 26063, 81334, 67768, 79695, 97030, 98339, 13077, 10987. 04085, 91337, 46414, 42822, 77263, 46594, 70474, 58784, 77872, 01927, 71528, 07317. 67907, 70715, 72134, 44730, 60570, 07334, 92436, 93113. 83504, 93163, 12840, 42512, 19256, 51798, 06941, 13528. 01314, 70130, 47816, 43788, 51852, 90928, 54520, 11658, 39341, 96562, 13491, 43415. 95625, 86586, 55705, 52690. 49652, 09858, 03385, 07224, 26482, 93972, 85847, 83163, 05777, 75606, 88876, 44624, 82468, 57926, 03953, 52773. 48030, 48029, 00587, 60758, 25104, 74709, 16439, 61362. 67604, 49256, 27420, 42083, 20856, 61190, 62545, 43372, 13153, 59584, 50687, 72460. 2901618766 79524 06163 42522 57719 54291 62981 93064 55377 99140 37340 43287 52628 88963 99587 94757 29174 64263 57455 25407 90914 51357 11136 94109 11939 32519 10760 20825 20261 87985 31887 70584 29725 91677 81314 96990 09019 21169 71737 27847 68472 68608 49003 37702 42429 16513 00500 51683 23364 35038 95170 29813 92233 45172 20138 12806 96501 17844 08745 19601 21228 51937 16231 30171 14448 46409 03890 64495 44400 61986 90754 85160 26327 50529 83491 87407 86680 88183 38510 22833 45085 04860 82503 93021 33219 71551 84306 35455 00766 82829 49304 13776 55279 39751 75461 39539 84683 39363 83047 46119 96653 85815 38420 56853 38621 86725 23340 28308 71123 28278 92125 07712 62946 32295 63989 89893 58211 67456 27010 21835 64622 01349 67151 88190 97303 81198 00497 34072 39610 36854 06643 19395 09790 19069 96395 52453 00545 05806 85501 95673 02292 19139 33918 56803 44903 98205 95510 02263 53536 19204 19947 45538 59381 wait, no, yeah, that was okay. 02343 95544 95977 83779 02374 21617 27111 72364 34354 39478 22181 85286 24085 14006 66044 33258 88569 86705 43154 70696 57474 58550 33232 33421 07301 54594 05165 53790 68662 73237 99585 11562 57843 22988 27372 31989 87571 41595 78111 96358 33005 94087 30681 21602 87649-62867.
One in 10.
Well, it's not written on here, so we can't show it. It's
I actually do know the next digit is 4. It's just not on there.
Yeah.
So,
Bravo.
with that, thank you all so much for coming to the Cornell Astronomical Society Pi Day celebration. I guess if any of you do have questions after that, I can try to answer some of those. And I know I made a couple mistakes. I saw you marking them down, so we'll review those. But yeah.
Is the Pi, like, you caught yourself every mistake that I saw, is the Pi Federation okay with that?
No, unfortunately. I was basically expecting, like the way I plan to actually submit it to the website is when I'm back home for spring break. There was a website, it seems to be down now, like as of just a couple days ago. Hopefully they bring it back, where you can type in like 100 digits at a time and then like press return and it'll verify that. So that's that sort of actually allows me to check each 100 more carefully before I press enter. But yeah. Yeah. So what were you gonna say something?
Swag.
Swag? Yeah. Yeah.
Interestingly, I don't think you made any mistakes on the last 1,000.
No, I know I did. I think I did at least, or I corrected myself at
You
least.
made one digit wrong last.
Most of the mistakes that you corrected, I think, are.
Awesome. Okay.
I didn't mark anything wrong.
Oh. Well, that might have been useful, I guess, if we wanted to see how far I got without making a mistake.
Also, I have a pen today.
But we can also take the, we don't really need the markings anyway, because we have the recording.
Yeah.
So yeah.
Find that I don't.
My brain frame rate is not.
Yeah,
Those
number,
names.
I wasn't sure if it was the number or not, because I just couldn't process doing that fast.
Yeah, but then if you think about it, you could go back and look at it and then you're already like 2 moves ahead. That's true, I'm gonna lie. But I'm happy to check you against an arbitrary list of digits because it is functionally the same.
Yeah. Well, I think I will end the Zoom event unless there's messages in chat. Oh, it's just, yeah, hello, thank you. Yeah, so, you all are free to leave the room now. And have a great rest of the night.
I think it's.